So now you can see that multiple assembly instructions actually make up single instruction lines in C. Now what can we do? The first solution, can we just disable and enable all the interrupts? So now let's think about hardware interrupts now. Say we just disable and enable it so that we don't have any conflicts here. So but interrupts are there for a reason and have this highest priority. So you should use this sparingly, and actually good programming avoids this at all costs. So don't do it. Another solution. Well, can we maybe use the idea of a global lock? So global lock, you do this, global unlock. Here global lock, global unlock. Well, this actually can lead to deadlock as well. So the hardware events that cause an ISR can happen literally anywhere. You did not disable any interrupts, so they can happen right in here as well. And they can then wait for the resource to be available, but it was locked. So this does not prevent deadlock. So let's talk about semaphores. So as when we talk about locks, right? What can actually happen then? So let's have a deeper look at how two tasks with different priorities are executing. So the context switched in and out by the operating system because of their priorities. But there's also these semaphores that lock resources. And before I already talked about priority inversion in an earlier lecture. But here we see it again. And take this particular low priority task 2 and a high priority task 1. So say this one is running, so it means running. And then at some point it needs to it locks a resource. So it's running with a semaphore. It runs. But now a slightly high priority task, is going, like this guy, task 1, is now context switched in by the operating system, but the lock is still held by this other task that is context switched out. So yeah, you can keep on running until it attempts to get access to that resource that is locked by the semaphore, right? Now that means that you are blocked, so you cannot do anything. So that means that you are context switched out, and therefore this lower priority task must finish to the point where it releases the lock. Once it is released, then it is context switched out again, and now this other task can get hold of that shared resource and can now finish to completion. And say at this, in this example we have something else happening, maybe why this is blocked. But the point is, we see what we call a priority inversion, which is even more clear in this example, where we have 3 tasks. So we still have this task over here and the higher task over here. But it is also possible that the low priority task is getting the lock, holding the lock for that resource, is computing, and it gets context switched out, as we said, by this higher task. It starts computing and then it wants to get that resource, but it doesn't get any access to it, so it's blocked. So it's context switched out, and this low priority task starts executing. And then some medium task is kicking this task out and starts executing, which means that this high priority task has to wait even longer for this lower priority task to finish unlocking that resource. So that can be done, that's like what we call unbounded priority inversion. There's no bound on this. It could keep on going like that. So the high priority task effectively has gotten the priority of the lowest priority task. Therefore we call it priority inversion. So priority in inheritance, right, we talked about that, is where we get a little bit, the operating system starts to change the priority level of the low priority task to the higher priority in order to get it unbounded priority inversion to eliminate that. So here it is. You run, you lock. It gets kicked out because high priority task is running, but oops, it needs that resource, so it's blocked. Now the operating system says this task inherits the high priority of that task so that it can complete the execution till it releases the lock. After that it gets again its lower priority, which means that now the high priority gets the lock and can get access to the resource and run till completion. And no in the middle processes, medium priority processes, can get access, can kick this low priority task out because it inherited for this time period the high priority of the higher priority task. So that's pretty cool. So let's talk about the priority ceiling protocol. So here we're talking about two things. One is we have resources and we have processes. Processes, as we have seen, can have priorities, and we can also assign so here we say, so I'm searching for the word, that's why I'm hesitating, but we have each task has a priority, and each resource is associated with a semaphore, and a semaphore is also assigned what we call a ceiling priority, which is going to be greater than or equal to the maximum priority of all the tasks that use it. Alright, so that's the idea. So at runtime, a task assumes a priority equal to the static priority or the ceiling value of its resource, whatever is larger. In other words, you inherit the priority effectively of the highest priority task that uses that same resource, which means that you're going to finish that fast enough. Like you will not be interrupted by medium priority processes that will kick you out, and therefore you have this unbounded priority inversion. So if a task requires a resource, the priority of the task will be raised to the ceiling priority of the resource. That's what I just tried to explain. And now when the task releases the resource, the priority is reset to its original value. Now it can be shown that this scheme minimizes the time that the highest priority task will be blocked, and it eliminates the potential of deadlock. So that's kind of cool, and that's why I'm talking about it. So here we see a picture, a diagram with all kinds of stuff that happens. So let me see whether I can parse this myself. So let's see what happens. So we have task 0 up to task 3. So the priority is from low to high for each of those tasks. And what do we see here? So we have this at 1. We start with the lowest priority running, and all the others are blocked. Task 1, 2 and 0 are blocked. So what does that mean? It effectively means that we have inherited that ceiling priority because all the others are blocked. So at some point, number 2 over here, task 3 takes a semaphore and gets elevated to the ceiling priority. So that is what I just wanted to say, exactly. So it gets elevated to the ceiling priority, so it gets the highest priority. Alright, cool. The high priority task 0 unlocks and the RTOS switches. That is happening in 3, because this has a higher priority than the ceiling priority that was inherited by task 0, so it goes here, so it starts to execute. Now, so that was, so what is 4? In the meantime, okay, fine, over here, task 1 has unlocked blocked and is ready when the semaphore is available. So say it was blocked before for some reason, it's unblocked, it's ready to execute, and it's actually waiting for that semaphore to be available. Okay. Then at 5, over here, we see that task 0 runs to completion and blocks and effectively blocks again. The R2S switches back to task 3 over here because it gets effectively it has unlocked this, so it gets out. But what does that mean? So it goes back to task 3 at the ceiling priority, and then eventually at 6 over here, task 3 releases the semaphore and reverts to its lowest priority. So that's all in one go, right? This 5 to 6. So effectively, you're done with the computation, you unlock the semaphore, the priority gets reverted to the original priority, gets back to this point, and for that reason, task 1 can take over in 7 because it's a higher priority than task 3. So 5, 6 and 7 sort of happens pretty much all at the same moment, right? And task 1 is taking over the computation at 7. The remaining tasks run in priority order, so this completes and then that completes, for example, because this was unblocked, so it is ready to execute, and we assume here that this is blocked, so it's waiting for something else. So this is an example to how this priority inheritance through this priority ceiling protocol actually happens. Alright, so this is pretty much what I wanted to talk about, and we still have 2 lectures to go on real-time operating systems, so I hope to see you all there.